The video you're watching right now travels across miles and miles of cables at the bottom of our oceans through large data centers like this just to reach you. This complex harmony of events happens within a few seconds every single time you do anything over the internet. Computer networks has transformed much of our lives. It has made it possible to communicate instantaneously, to search up anything, and for you to make online purchases anywhere you are. Without computer networks, none of this would be possible. In this video, we'll demystify how they work. We'll start from the very beginning with networking devices and build up our understanding with the different protocols and concepts that make computer networks a reality. Networking devices comes in all shapes and sizes, and all kind of look the same. But fundamentally, they perform the same few tasks, which is either to send, receive, or to process data. Think of it like driving a car from one point to another. There are many different types of infrastructure that helps facilitate that process, which are what computer networks are designed to do. The destinations are like the devices you use, your phones, laptops, or servers. Servers are simply a system that provides resources and services to clients, whether that is to send emails or to store data. Devices have addresses as well, that being their MAC address. A MAC address is written as 6 groups of 2 hexadecimal numbers. It needs to be this long so that every device can have a unique MAC address, which is burned into the network card. When a device is connected to a network, it is also given an IP address. An IP address is made up of 4 sets of numbers, which can be from 0 to 255. This IP address is dynamic and is assigned based on the network it is connected to. IP addresses identify devices based on the part of the network it is in, whereas MAC addresses are random. We'll take a further look at them later on as there is much more to it, but for now, just know that IP addresses are dynamic and can change when you disconnect from your router, for example, but the MAC address will always remain the same. At the heart of our network, we have routers, which main purpose is to route packets of data between different networks. It does so by having an internal routing table of the addresses of the networks that are connected to it, allowing it to route packets that it receives. Routers also have additional features such as providing security, functioning as wireless access point, and assigning IP addresses, which we will look into later on. Imagine that the data packets are like planes trying to leave an airport. The air traffic controller in this case would be the router. It directs the plane on the most efficient way to leave and enter the airport, similar to how the router routes packets to leave and enter the network. Routers also create separate broadcast domains. When a device sends out the broadcast, all the devices in the broadcast domain will receive it. Devices need to send out broadcasts for many reasons, such as when a new device joins a network and needs to find the router, or to share routing information within the network. Separating the network using a router is necessary to reduce congestion. Another common networking device you will see is a switch. While a router connects multiple networks, a switch helps to connect the devices within the network, allowing them to communicate together. It also helps by providing more Ethernet ports. What makes a switch different as well is that it directs data based on the MAC address. So every time it receives data, it finds the MAC address in its MAC address table to be able to know which port to send the data out of. This MAC address table is filled by the data that the switch receives, sort of like a database of all the devices that are connected to it and their associated MAC addresses. Similar to switches, hubs are also networking devices that forward data within a network. The big difference is that they do not have a MAC address table to keep track of which devices are connected to which ports, so data is sent out of all ports regardless of the destination address. This makes it really inefficient and unsecure to use, and are therefore obsolete and are no longer used anymore. In a typical home setup, the router is also connected to a modem, which is what connects your home network to the internet through your internet service provider. Some routers also come in with built-in modems, making your setup just a tad bit cleaner. With so many devices, there are many ways you can connect them. Some are cheaper, while others are more reliable. This is called the network topology, which refers to the arrangement of devices, also known as nodes, within a network. The star topology is perhaps the most common and easiest to implement. This is where all data must pass through a central node, which could be a hub, switch, or router, to communicate with each other. Here, the advantage is that adding additional devices is easy, but comes at the cost of having a single point of failure, as if the central node stops working, then the devices will no longer be able to communicate with one another. On the contrary, a fully connected mesh topology involves connecting each device to every other device. This makes it extremely reliable, but comes at the cost of being expensive and impractical for large networks. Other common topologies include the ring topology, where devices are connected to one another, and the bus topology, where devices are connected to a central cable. Now that we've seen how devices can be connected, how exactly does data travel from one node to another? How is it transmitted? The answer lies in using binary. The data is transmitted as ones and zeros. If the devices were to be connected using Ethernet cables, that data is transmitted using electronic signals by sending high and low signals. Or if they were connected wirelessly, then that data is transmitted through radio waves. The devices encode and decode the data to be in this format because it is the most fundamental form of data that computers can actually work with. They can't work with text or regular numbers, which can't be transmitted either. Networks are usually categorized into a few types based on their size. If the network is contained within a small geographical area, it is a local area network. An example of this would be a small office or home network. The next step up will be a metropolitan area network, which refers to a network spread across several buildings. For example, if a company has multiple offices that are spread out across different buildings, but connected to the same network, that would make up a metropolitan area network. Simply put, it connects multiple LANs together. Lastly, there are wide area networks, which cover an even larger geographical area, covering countries and regions. The internet is the largest example of a wide area network, which connects many international networks made out of smaller networks. As we saw previously, IP addresses are assigned once the device connects to the network. Any data packet meant to travel through the internet contains an Internet Protocol header that includes the source and destination IP addresses. One of the problems with having so many devices on the internet is that there now isn't sufficient IP addresses to assign to every single device. For this reason, IP addresses are split up into two categories: private and public IP addresses. When a device is within a local network, it uses a private IP address, and before its data goes out of the network, the router replaces the source IP address with its own public IP address, while the destination IP address remains the same. This process is called network address translation, and the advantage is that fewer public IP addresses need to be allocated to devices, while allowing for more IP addresses to be used within the private network. Let's take a deeper look into IP addresses. When we see an address like 192.168.0.1, it is usually also associated with something called a subnet mask, like 255.255.255.0. From this, we can gain two pieces of information from it, the first being the network it is in, and the second being the number of devices allowed in the network. Using the same example, 192.168.0 would be the network address, meaning that all devices in this network will start with 192.168.0. Each of these parts can be any number from 0 to 255. The last portion is the host portion, and must be unique for each host within the network. This makes for a total of 256 possible addresses for this example, but only 254 of them can be assigned to hosts. This is because the first and last addresses are reserved, the first one being the network ID to identify the network in other networks, and the last address being the broadcast address that devices can use when they want to send a message to all devices within the network. The subnet mask is what separates the network portion from the host portion of a given IP address. We can identify this by converting both the IP address and subnet mask to binary, and the network portion is simply the part where the subnet masks are all ones, while the host portion is the part where it is all zeros. So, for example, given an IP address of 10.0.0.1 and a subnet mask of 255.0.0.0, we can immediately know that 10 is the network portion and the rest is the host portion, allowing a total of around 16 million possible IP addresses to be used within this network. This allows us to perform subnetting, meaning to split up the network, which is incredibly useful. For example, if a company wants to apply certain rules to different departments it has, then it will need to create different subnets to split up their network. Currently, addresses like the ones we saw are IPv4 addresses. But to increase the address space, a new version, IPv6, is currently in the process of being implemented. IPv6 addresses are made up of 8 groups of 4 hexadecimal digits, which can create way more possible addresses than IPv4. Devices and topologies describe how computer networks communicate, but what about the methods they use to communicate? This is where protocols come in. Simply put, protocols define the rules of how devices should communicate. They come in the form of acronyms made up of a few letters and may seem mysterious when you first encounter them. But if you view them simply as a set of rules, then it becomes pretty simple. These rules include things like how devices should make requests, how their data is formatted and acknowledged, what data should that packet headers contain, and what to do when things go wrong, how missing data should be dealt with, for example. There are different protocols being used when you visit a website, when you connect to a Bluetooth device, or when you connect to your router. It is important to keep in mind that protocols can also be used on top of one another. When you make a request to a website, your device uses the Internet Protocol, another protocol to communicate with the web server, and another protocol that defines how the data you send and receive should be formatted. All these different protocols modify the original data to produce the final result, which is then sent out by the source. We'll take a deeper look into this later on when we look at the OSI model, which provides a common framework for how these layers should work. And generally, these protocols can be divided into three categories, that being for communication, network management, and security. We'll go over the most common ones in this video. In communication, the most common protocol is the Transmission Control Protocol, TCP. It provides a set of rules for how devices on a network should exchange data, and is usually used in conjunction with other protocols such as HTTPS when you visit a website. Its job is to make sure that data gets sent to the recipient correctly and that any data that gets lost is retransmitted. TCP works by first initiating a connection between the two devices through a three-way handshake, where the initiating client sends a synchronization SYN request to start the connection. The server then acknowledges by setting the ACK flag and sets the SYN flag as well. Finally, the client acknowledges this by sending a request with the ACK flag. Now, when the client is ready to send data, the data is broken up into different packets to avoid overwhelming the network. TCP also requires important information to be placed inside the header. This includes things like a checksum, which is calculated based on the data, TCP and IP header using an algorithm so the receiver can perform the same calculation and verify that the data hasn't been corrupted. There's also the source and destination port numbers. Think of port numbers like unit numbers for different units within a building. If a letter had the building's address, the unit number identifies which particular unit it is meant for. Similarly, port numbers are used to virtually identify which application the data is meant for within the device, while the IP and MAC address identifies which device it is for. There are predefined port numbers for services such as HTTP, which uses port number 80. This means that if I want to make an HTTP request to a server, my device will set the destination port number to 80, while the source port number can be any available one on my device. There is also the sequence number, which is used to track how much data in bytes that the device has successfully sent. Then there is the acknowledgement number, used to track how much data the device has successfully received. For example, if my device were to send the server 100 bytes of data, it will send a response with an acknowledgement number incremented by 100. If my device then sends 200 bytes of data next, it will increment the sequence number by 100 because it knows that that is the amount of data that has been successfully delivered so far, and the cycle repeats until both devices are done sending data. There are multiple reasons why we need these two numbers. Firstly, the sequence number helps to put the data back together since it was splitted out by the sender. The sender can also know if the receiver doesn't receive a certain packet if it doesn't receive the acknowledgement number for it. After a certain period of time, the sender will automatically retransmit it. These features of TCP helps ensure that the data is sent and received correctly and remains error-free, just like what you get when you pay a little bit more for registered mail. The compromise that is made is that because of all of these extra steps, like acknowledging every packet and adding more metadata, is that TCP uses more bandwidth and is slower. On the other hand, we have an alternative protocol, UDP, the User Datagram Protocol. This functions just like unregistered mail. Packets are sent without having to be acknowledged, and there are no handshakes to initialize the connection or error checking procedures. The UDP header only includes the source and destination port number, a checksum for the receiver to verify the data, and the total length of the UDP segment. This makes UDP extremely unreliable and is only used in a few scenarios such as video streaming, in games, and generally live data where speed is important and the cost of potentially missing data is acceptable. Now, we'll look more into protocols used to achieve specific tasks, the first of which being the Hypertext Transfer Protocol, HTTP, which sets the rules for how resources such as web pages are sent and received on the internet. When you click on this video, HTTP defines how your browser should make that request and the format of the response that it should expect. If you want to dive even deeper, the original full specification can be found here. This long document specifies things like how the request should contain the HTTP version, the URL, a HTTP method, headers, and an optional body. It goes into extreme detail over what each of these means, like how a URL is structured, what methods are there, and what are the available HTTP response status codes. Although HTTP is for the most part replaced by the HTTPS protocol, as HTTP is sent in clear text, allowing intermediate devices to view the information you send and receive from a web server. HTTPS solves this problem by encrypting the data while it is in transit. Other common communication protocols include the Simple Mail Transfer Protocol (SMTP), used to send emails, as well as the Secure Shell Protocol (SSH), which makes it possible to remotely send commands to other computers. On the other hand, there are also protocols used for managing the network. As we saw previously, whenever a device connects to a network, an IP address is assigned to it. This is possible due to the Dynamic Host Configuration Protocol (DHCP). In home networks, the DHCP server is usually the router. When a device is connected to a network, it sends a broadcast message. The DHCP server then responds with an offer to the device with an IP address based on a predefined scope. Besides that, it also offers the DNS address, subnet mask, and default gateway address. The default gateway is simply the device that your client sends data to that are meant to leave the local network. This is usually the router, since it has the job of connecting your local network to the internet. The DHCP server only leases the IP address, usually for about a day. This is so if the device were to be disconnected, the IP address can be freed and used for another device. But if the device were to stay connected, it can send a request to renew the IP address. Now, let's turn to a common application we use. When you enter a URL, how does your device know the IP address of the web server it is for? This is possible due to the domain name system, the DNS protocol. It functions similarly to a phone book. When you want to contact someone, you only remember their name but not their phone number. Just like when you visit a website, you remember the domain name but not the IP address of the web server. The DNS resolution process is a complex one. When you enter in a domain name to visit a website, your browser looks at the cache on your device to see if it can locate the IP address associated with it. If not, it sends a request to the local DNS resolver, which is provided by your internet service provider. If the local DNS resolver doesn't have the IP address in its cache either, then it makes multiple calls to different DNS servers to reach the authoritative name servers which hold the DNS records for that particular domain. These different parts of a computer network can be kind of confusing, especially about how they all work together. So let's take a look at the OSI model, a framework consisting of 7 layers used to describe how different parts of a network should function together. At the top, we have layers 5 to 7, which performs the task that we're most concerned about. The main objective being to allow you, the user, to use software such as web browsers, email clients, and file sharing by formatting requests and responses according to protocols such as HTTPS, SMTP, and FTP. On the next layer down, we have the transport layer, responsible for ensuring that the data transmission is reliable, performing error correction, and flow control between devices in a network by adding data such as checksums, using protocols such as TCP and UDP. Layer 3 is the network layer. The data unit at this layer is a packet, which uses IP addresses to identify devices. Here, information is added to route data between multiple networks, such as the source and destination IP addresses. Next up is the data link layer. Here, data is referred to as frames. Frames use MAC addresses to identify devices instead of IP addresses. Frames add information to route data within a local network, such as the source and destination MAC addresses. Finally, the first layer is the physical layer. Here, the combined data of all the previous layers is then converted and transmitted in ones and zeros like we saw previously, using electronic signals, radio waves, or light signals. All these layers modify the original data, each layer adding their own headers with specific information to achieve their purpose. For example, switches only use the layer 2 headers, while routers use the layer 3 headers. The receiver then unpacks all of that data for the application it was meant for. This is just like if you wanted to send a gift. You wrap it up in a box and add the tracking label. At the different fulfillment centers that it passes through, they add their barcodes to identify the parcel internally. When the recipient receives it, they unwrap all of these layers to find the original gift. The reason why the OSI model exists is simply to provide a standardized way of how a network should function. This way, routers from one manufacturer can work with another. The most common use case is if you need to troubleshoot a problem, where you can work through the layers independently to isolate the problem. That's all for this video. If it has helped, you'll probably enjoy watching this video next. Besides that, please consider possibly also liking and subscribing to my channel for more of such content.